Okay, so I want to discuss the crystallization kinetics using the Avrami equation. So this is a section that I added on in addition to the previous recordings that I didn't cover the Avrami equation, and I think that you should know about Bayesian languages and Avrami equation. When it gets to the details, it's pretty complex, but I would like to give an overview on this. So in the 1940s, the Melvin Avrami, 1940s, and then Melvin Avrami, he's in Columbia University. He published a paper on essentially general theory on phase transition kinetics, whether it's a homogeneous or heterogeneous nucleation, and depending on the dimensionality. So he assumed this very simple model that crystal grow in 3 dimensions at a constant rate, and then with an assumption that he was able to get some simple equation, and later people adapt that, and essentially 1950s, and the polymer crystallization, polymer crystal study has been done in the field. So I want to use this section as a chance for me to discuss actually what is known as a crystallinity. Okay, so this is an equation in the 1719 in your textbook, which is this is simply the WL is a weight of amorphous liquid. Okay, so and then the weight knot is, I guess, the weight is a weight of I guess this is an initial weight of sample. And also what that means is this initial weight is composed of the weight of liquid and the weight of solid, which is a weight of crystalline solid. Okay? So this is a notation that Avrami used, and many people still using it. And what you can see from here is essentially we can, this is a wave fraction of amorphous. And crystalline fraction, which is also known as a crystallinity, is nothing, it's just simply shown as like this. So it can be shown as e to the constant z to the n. Okay. Sometimes the people use a different constant notation, but it's this Avrami exponent n has a very generic meaning. Okay. So there are experimental technique, and if you can measure the essentially degree of crystallinity at different times of, let's say, isothermal crystallization, and you can essentially get these two values, the Avrami constant z, sometimes they call it k, and Avrami exponent a, n. N is Avrami exponent. And a lot of meanings are in there, and this is used still quite well these days when you study the crystallization. And the first one, the technique that how we can measure the Kc, how we can quantify Kc. The one way is essentially the technical, the differential scanning calorimetry. I think that I mentioned to you about the delta H melting, heat of fusion, heat of melting for a sample can be measured based on the essentially the area under the curve and the melting peak, and then versus you can also looking at heat of fusion for 100% crystal for any polymers. So if you have a sample that you know that what is the value for that, and this is what you measure, and in the DSC experiment, crystallinity can be defined as simply delta M H of a sample normalized by the one with 100% crystal. Okay. So then all you got to do is to find the known values. So for the one with the polyethylene, the delta melting for 100% crystal known as 293 joule per gram. Okay. For isotactic polypropylene, delta H melting for 100% crystal is 209 joule per gram. Okay, so you can use this is probably the most popular one because DSC is readily available and you can use it pretty easily. The second method that people use is wide-angle X-ray scattering. Okay, and actually you can see this equation. Let me look at this textbook. I remember seeing these figures. It's in the textbook figure. Yeah, there we go. That's the textbook figure 17. Okay, that's in page 417. Okay, and so by the way, the Avrami equation is discussed in the crystallization process. Was discussed. This whole thing is discussed. Avrami equation, and it's discussed in section 17.7, page 428. Okay, of this text. So if you do the wide-angle X-ray scattering, and this is a angle, and then you will see essentially this is a typical figure that was shown up in the demonstrated in the textbook. So what that means is here from this area under the curve, this is the amorphous halo, and those are the area. So we are talking about the area. There's an area from the crystalline regions. So the crystallinity is area in the crystal from the crystalline region, from area from amorphous, and area for crystallinity. So that's an equation number 17-11 in the textbook. There is a third method, which is what is called the dilatometry. So this is the one you're measuring the volume change, and so the volume changes you can put it in using the mercury dilatometer, and this is before the invention of the DSCs are easily accessible. Dilatometry was a most common technique. They can measure the initial volume. This is an initial volume, and then they can measure this is a final. What that means, the time is infinity, final volume, and then volume, time equal t. And then because they are essentially this whole dilatometer, you are putting the sample in the measuring the volume through the capillary tube, and this whole thing is immersed in a temperature control bath, and then this is your sample, and they are measuring the height changes through the dilatometer, and then this is what they call mercury dilatometer, and they were able to measure the volume change easily using this technique. It is a very old-fashioned technique that not many people using it, but let's just say that by measuring the height changes from the capillary, you can essentially measure the volume of this polymer, as highlighted here, when you change the temperatures or maintain the temperatures. And as you can imagine that polymer has a different, the crystalline region has a different density compared to the amorphous region, so there was a volume change due to the crystallization. And this one is now related to height, which is in principle that's the experimental variable because of constant diameter of capillary in the dilatometer. And the relationship, this one is actually discussed in the text, and this is essentially shown up as an equation. As you can imagine, that this is Avrami exponential equation, and this quantity is related to amorphous. Okay, so once again, from here you can see that this is a 1 minus pi c is exponential minus constant to the Avrami exponent n. Okay. In the original Avrami derivation in the text, actually this was derived in a way. Amorphous weight fraction was e to the minus z t to the 4. So in this case, n is 4, and that's essentially general case, which is n is 4 is related to three-dimensional growth, and then there's a homogeneous nucleation. Okay, so there was an idea before, and then this exponent 4 was later changed into some different types of crystallization process, and then they get this name. So this is an Avrami, once again, Avrami equation, and you can get this one based on the DSC, wide-angle X-ray. Actually, this is much common than the dilatometer. In the textbook, is actually they show this data of showing log 1 minus pi c. Okay, so this is essentially same as 1 minus pi c. So they plot this value here, but so therefore you can use this idea. This is a amorphous fraction in a log scale, and then put this log scale onto the time. And then when they plot this, they will find us this slope is essentially n. Okay, the slope here is an exponent n, and they were able to, you can experimentally verify those. So what is the meaning of Avrami exponent n? Okay, here this is a table that shows to you that when Avrami exponent is 4, and you are talking about three-dimensional growth, and then there is a random nucleation. Random nucleation means essentially homogeneous nucleation. You do not put anything for such as a nucleating agent. So homogeneous nucleation. But now, because N can be measured from the log 1 minus crystallinity to the log to the t from the slope, you can calculate N. Sometimes N can have different values other than 4. And in the case of N is 3, there's a two case of scenario is possible. Okay. So this is when N is 3. One is still spherulite growth, but instantaneous nucleation. Instantaneous nucleation means heterogeneous nucleation. Okay? So you are putting a nucleating agent or something that actually trigger the nucleation very easily, and that's the case. Or sometimes but this N3 also means the crystallization can happen in a two-dimensional way, and then is an homogeneous nucleation. Okay, so you can see that it ranges for some of the dimensionality and what is called the types of kinetic order of the nucleation. So N is essentially depends on first the dimensionality of the crystal growth. Okay, so 3 is for spherulite. 2 means disc-like, and 1 means rod-like. Something that is close to rod-like crystallization, do you remember the shish kebab? And that's something close to the rod-like one, but it is a combination of disc-like to the rod-like. So depending on their crystal growth and however you monitor the crystallization process, this N gives that idea. And plus 2 is, like I said, whether it's a homogeneous. In here the table says random versus heterogeneous, which is instantaneous, which means fast. Nucleation. So it's a combination of the new understanding of nucleation process and the growth. Okay, the growth, how the growth occurs and how the nucleation can occur, and this is the one that, which is that's the case is for homogeneous is 1, adding 2, and this is a 0. So that's the ranges. And also this Avrami equation for the evaluation of these two, number 2, there's actually assumption. Their main assumption is this Avrami equation is good for early stage of crystal growth. You can imagine that when the crystal grows, they can grow like this as time goes on. Toward the later stages, and they are bumping into each other, right? Eventually, later stages, they will start to form this faceted crystal that you don't want to lead it into this much. So the good rule of thumb is up to probably crystallinity less than 30%, that will be a good thing. Another assumption that this Avrami equation is actually it's called a uniform growth rate. So the R is, let's say, the size, crystal radius is actually multiplied by the mu times t, and this is actually equation 1713 in your textbook. And this term mu is what we call it as, this one we call growth rate constant. Okay, and then this is used to be, and they actually show this textbook shows a dependence of crystal growth rate mu when you change your crystallization temperature for this polymer. That has a different molecular weight. Okay, molar mass is different. So how the molar mass is different, and you can see that it's also affected by the molar mass. So the higher the lower the molecular weight it is, the faster the crystal can grow because of the lower viscosity. So there's a less friction to move this polymer chains around to develop the crystal domains. Okay, so by this depends on the molecular weight, but it is a fixed value. Okay, fixed value for a given temperature of crystallization, and also the temperature of the molecular weight of the sample that you already have. And then I look at the information more about this information is not easy to find in the textbook, so I look at the literatures who reported the Avrami exponent n for the different polymers, and you will see this paper, and these are the different polymers: polyethylene, polypropylene. They have different values. Okay, so these are the values that the ranges can changes from the even smaller than 3, and so they have reported these values. Sometimes the polyethylene oxide is even lower, right? The N is 2 means it is more like a homogeneous nucleation and disc-like growth, or more like a fibrilla with the heterogeneous nucleation. But this is really an example, and then I'm pretty sure there's a lot more different kinds of way. So the comments on the Avrami exponent is you can essentially kind of infer from the Avrami equation n, and that gives an idea about how the crystal grow. And then this is one that I find out from one of the notes available from the internet. And then essentially you don't have to look at, okay? Although you cannot see this, the crystal growth, you can still have an idea about how crystal may have occurred, and using the essentially DSC, for example, right? You don't see the crystal growth. You're just looking at the measure the crystallinity at different stages, different time of crystallization, and you can find out the mechanism that can be understood. Okay. And this is the assumption here is also the uniform growth rate it may not be the good one, because as the polymer the crystal grows from the inside out, and they are not the same, and the density also may not be the same. So this is another thing that there is a lot of assumption that it may not be so valid for the polymers, because if you're looking at the spherulite, growing out, the crystal growing out from the earlier stages, the density here and the density outside may not be the same. So higher in the internal region. So it is also time dependent, the density itself. So there is a uniform density is also assumed in here. So but I wanted to introduce this topic on the Avrami equation to study the crystal growth, because this just to give you a right starting point on the languages. There's an effort for people to study the essentially crystallization kinetics and trying to understand the mechanism for how the crystal grow in three-dimensional way, or even geometrically restricted way involved in this.